Welcome back, everyone, to this continued discussion of support vector machines. Now we're going to take a look at how to perform a regression with scikit-learn with support vector machines. That is, using support vector machines to predict a continuous label. The ideas behind support vector regression are very similar to the ideas behind support vector classification. But in this case, what we really want is a model that can predict a continuous label given some set of features. In this example, we see a bunch of data points for a single feature x, and then the output that we actually want to be able to predict, which is y. And what support vector regression does is it uses the margins, just as we did before, to try to connect with the support vectors in this data set to get the best fit model possible. That way this model can in the future be used to actually predict a continuous label. That is, for some new value of x, we can go ahead and check what the support vector regression thinks the output y should be. Again, we're now predicting a continuous label, which means we actually don't care too much about what side of the margins the points are actually on. We just care that the model is able to use the margins to get a best fit to the actual data. Now, for this example, we're going to be checking out a data set using a concrete slump test. If you're not familiar with a concrete slump test, what it does is it measures the consistency of fresh concrete before it actually sets. And it's performed to check the workability of freshly made concrete, and therefore the ease with which concrete flows. It can also be used as an indicator of an improperly mixed batch. The way it works, as shown in the top diagram, is you mix a fresh batch of cement and then put it in a bucket, and then flip over that bucket onto a flat surface and pull the bucket off. And then, in the bottom diagram, you can see the potential options, and this is where the slump, so to speak, occurs. If it's too wet, then you have a very large slump. That means that most of it has collapsed. If it's too dry, that means you have a very small slump. That is the distance from the original bottom or top of the bucket to the actual remaining cement. Just right, you should see some sort of measurement of slump. There is also a measurement of flow in our data set. Both of these are measured in centimeters. Now, our data set is going to consist of a variety of cement properties and then the resulting slump test metrics in centimeters. Later on, that set concrete was actually tested for compressive strength 28 days later. The main idea behind all of this is to say if we have a data set that has the input variables that we're actually putting into the fresh concrete, things like the amount of water versus coarse aggregate or fine aggregate, and we also have the results of the slump test, that is the centimeters of slump and centimeters of flow, can we predict the 28-day compressive strength later just knowing the input variables themselves the day we actually mix the concrete? So what we have in the data set are a bunch of different slump test results for a bunch of different mix of cement, slag, fly ash, water, etc. That is the components that are going into these concrete samples that we did a slump test on. Then hopefully in the future, we can actually use our regression model to try to predict the compressive strength of a variety of mixture of components before we have to actually physically mix those. Let's head over to the Jupyter Notebook and check out this data set as well. Then we'll perform a regression analysis with support vector machines. I'm going to head to the notebook now. Okay, here I am at my notebook. I've already imported NumPy, Pandas, Seaborn, and Matplotlib.pyplot. Now it's time to read in the data set. I'll say df is equal to pd.readCSV, and then in your data folder, there is a data file called cementslump.csv. And if we check out the head of this data frame, it essentially consists of a variety of components that we actually mix into the concrete, that is cement, slag, fly ash, water, SP, coarse aggregate versus fine aggregate, and then you have the results of the slump and flow from the slump test, and these are measured in centimeters. And then finally, we have the predictive label that we want to be able to create a model of, which is the compressive strength of this particular concrete mix 28 days later. So what happened is we have the components of the concrete mix itself, and then we do a slump test with that concrete, get some measurements of slump and flow in centimeters, and then finally, 28 days later, they took a compressive strength once it had completely dried. So now what we want to be able to do is for any batch that we freshly mix, we can hopefully then predict what its compressive strength is going to be based off the results of its slump test and the components that are mixed into that fresh concrete batch. So what we can do here is check out the relationship between the label as far as correlation is concerned. So what we can do is say something like SNS heat map, say df correlation, run that, and this should show you then a correlation, and then we can also label this. So if you recall off SNS heat map, you can annotate, set it equal to true. So you can say annotate is true, and then off of this we can also say PLT figure, make the fig size a little larger. Maybe make this 8 by 8, and then DPI equal to 200, just to make it a little sharper. You run that, and then I can see the actual correlations. So really, the main correlation I'm probably most interested in is the one with this compressive strength. That's the label I'm trying to predict. And essentially what I don't want is a bunch of zeros here. I'm okay with really strong negative correlations and really strong positive correlations. And it looks like this data set does have quite a bit of signal here. So what we're going to be able to hopefully do is create a model based off these features in order to predict the compressive strength of that particular wet concrete mix after we've taken into account what components are in it, as well as the results of the slump test. So what I want to do is start off with my train test split. And if you want, you could alternatively start setting this up as a pipeline. And you can check out the lecture notebook that explains how to set it up as a pipeline, but we'll separate out the steps for now, just to make sure that we don't skip anything. So I first want to separate out the features from the label. So we'll say, in fact, we can do this by saying df columns. It's kind of a faster way to do it. And then I can grab this column name, which is compressive space strength space 28 days megapascals. So we just have to make sure we spell this exactly right. That way I can say x is equal to df drop, and then I'm going to drop that column along axis is equal to 1 for my features, which means y is equal to df, and then it's that column, the compressive strength. Now that I have my x and y, I want to perform my train test split. So we're going to say from scikit-learn.modelSelection import train test split. And then we call it train test split just as we did before. Expand on this, and then I'm going to, as we always do, just copy and paste this quick line to make sure I get the tuple unpacking correct. So I'm going to copy this, paste it in here, and then we're going to split up x and y. And for this particular case, in order to match up everything, I'm going to set test size is equal to 0.3 and the random state as 101. That way you get the same split I do for the same test size. Now what's absolutely key here is recall support vector machines really looks at the feature space. And with the use of kernels, we could be expanding this feature space as well. Whenever you're dealing with any sort of machine learning algorithm that really starts to look at the geometries of the feature space, you want to make sure that you scale your data. If you're not sure if your algorithm is going to be affected by it, you might as well just scale it anyways, since it won't negatively harm your model. So for support vector machines, it's really recommended that you scale your data first. Let's go ahead and do that. We'll say from sklearn.preprocessing, import standard scalar, create that scalar object, so an instance of standard scalar, and then we'll create instances of scaled xtrain. So that's a scalar fit. In fact, we can just call fit transform for xtrain to save an extra step. And then recall for scaled xtest, we don't want any data leakage, so all we're going to say is transform xtest. Okay, so as I just mentioned, for support vector machines, whether it's classification or regression, make sure you remember to scale your data. It's pretty much a must do for support vector machines. Now it's time to explore support vector machines for regression. And the way we import this is we say from sklearn.svm, it's still in the same family of models, and there's actually quite a variety of models you can work with. One of them is SVR, which is kind of the most generic version of support vector regression. And then there's also linear SVR, and linear SVR provides a faster implementation of support vector regression, but the caveat being it can only consider a linear kernel. So if you already know that you're going to be using a linear kernel, you should use linear SVR because mathematically it can perform a faster computation than just the normal SVR. However, if you want to explore the options of different kernels, such as the radial basis function, then you'll have to use SVR. So keep that in mind. Linear SVR can only work with a linear kernel, but it is faster than SVR. SVR, however, due to it being slower, can actually perform different calculations for different kernels. Now, let's go ahead and call help on SVR just to understand the parameters we can play with a little better. So you notice that we have this SVR, and it's going to be able to take in a kernel option, just as we've seen before, and then you have degree and gamma, just as we saw with classification. And recall, some of these only pertain to certain kernels, like degrees for polynomial kernel. And then you should also notice there is a C parameter, which is the regularization parameter. The C parameter is 1 by default, and often that's a reasonable default choice. If you have a lot of noisy observations, you should probably decrease it, as decreasing C corresponds to more regularization. Recall, decreasing C responds to more regularization because C is inversely proportional to the C we saw in the equations. Now, the other thing to note here is epsilon, and epsilon is something we haven't really seen before. Now, epsilon is actually a pretty easy parameter to understand. It essentially denotes how much error you're willing to allow per training data instance. So if you set epsilon to 0, that means you're saying the maximum allowable error per training data instance is 0. And that could lead to overfitting. So you do want to have usually some sort of positive epsilon value. The default here is 0.1, but it's really hard to have some sort of intuition, especially when you're dealing with kernels in higher feature spaces, and the fact that we have more than just a feature set of 2 features, we have many features. What we can do instead is just do a grid search for the best C parameter and best epsilon parameter, as well as maybe the best kernel or degree, etc. Lots of different things we can play around here. In general, just let the computer do the work and use cross-validation and a grid search to figure out the best or optimal parameters. Okay, so we have SVR ready to go. In order to actually do this, what we need to say is create a base model of SVR. And let's just try a base model with all the base or default parameters and see how it performs. And then what we can do is run a grid search in an attempt for a better model. I'm going to say base model dot fit, and let's fit this to the scaled X train data along with the Y train data. So I'm going to fit my default model here, and then I'm going to say my base predictions are equal to base model dot predict off the scaled X test. Now recall, we're performing a regression task, which means my metrics should be those for a continuous label, such as root mean squared error or mean absolute error. Let's evaluate the base model's performance before we perform a grid search. We will say from scikit-learn.metrics, import mean absolute error, say mean, there we go, and then mean squared error. Okay, so we're going to say our mean absolute error is going to be equal to y test versus our base model predictions. And right off the bat, our mean absolute error is 5.2. Recall that the units here are megapascals. And then what we're also going to check out is the root mean squared error. So that's NP square root of the mean squared error for y test against the base predictions. And that's 6.69. And to get an idea of the ranges we had in our original test set, we can say y test mean is 36. So hopefully that gives you an idea of what these values are kind of in the ballpark of. Since our average mean value was 36.2 megapascals, we have a mean absolute error of 5.2 and a root mean squared error of 6.69. Now, is that good or bad? Obviously, it depends on all the details, the previous work, what sort of compressing strength errors we're trying to actually obtain in this analysis, and your domain experience with concrete and slump tests, etc. For this particular case in this lecture, what I really want to know is, can I improve on this? This is the base model with the default parameters. Can I actually perform a grid search that can hopefully perform better than what we see here? So what we're going to go ahead and do is the following. I'll set up my parameter grid. We will say param grid is equal to, and then I can check out a variety of C values. So we can start off maybe close to 0, like 0.01 or 0.001, and kind of build off from there, which is kind of common to do. And then maybe if you want later, you can hone in on a certain regularization parameter. We can also start playing around with different kernels. So I can say kernel, make sure that's a string, kernel, and then we can try a linear kernel, a RBF kernel, radial basis function kernel, and then maybe even a polynomial kernel. And recall from our previous discussions, when it comes to something like the radial basis function, we have the option to set a gamma, and by default it's set as 1 over the number of features times x variance. So we'll say gamma, and we'll check out both the string codes, the scale string code and the auto string code. You could, if you want, pass in floating point values, but that's usually really hard to ascertain a range of those. What you could do is ascertain a range around the values for scalar auto. Recall that that's actually formulated if you take a look at help again. Let's go ahead and run this and scroll down. Recall that gamma, it was this scale auto. So maybe if you want to start your own floating point values, you can range those floating point values around this calculation or around 1 over n features. Kind of up to you. But for our case, we'll just test out those two strings. They should be pretty reasonable values to choose from. Since we have poly as an option, we should also set degree as something we explore. Keep in mind, for some of these kernels, like linear kernel, is not going to use degree. So as you're running your cross-validation, you may get some sort of warning saying degree ignored because you're using linear kernel. That's totally okay, and that's to be expected. So let's do, let's say, 2, 3, and 4. We'll do too many here, otherwise you'll kind of spend all day calculating. And then finally, if you want, you can also start to explore epsilon values. So epsilon, and as I mentioned, epsilon is the error you're willing to allow per training data instance. So something you can do is kind of start with 0 and then gradually work up to some higher level. So you can say 0, probably going to fit or overfit if you allow for no error. And then from this, you can slowly build it up as a larger and larger acceptable error. So we'll say 0.01, 0.1, and then maybe go to 0.5, 1, and then 2. Obviously, you can always check more. Or if you start to get good results, maybe around 0.5, expand in a new parameter search around 0.5 or something like that. But we have a large enough parameter grid, I think, in order to explore this. We'll say from scikit-learn.modelSelection, import the grid search CV. And now we're going to perform cross-validation on that training set. So I'll say my SVR, essentially it's the base model again. And then I'm going to say grid is equal to a grid search, CV, on this base SVR model, where I pass in my parameter grid, create that, and now it's time to fit the model. Whoops. I'm going to say grid fit, and I pass in my scaled xtrain and ytrain. Go ahead and run that, and if you want, you could add also verbose arguments when you're setting up your grid search, especially if it's going to be a very large grid search. But since this is a relatively small data set, it shouldn't take too long to actually do the grid search itself. Let's check out the best parameters that it was able to find. We'll say grid best params, run that, and it looks like it decided a regularization value of 1, degree of 2 with epsilon 2, gamma scale, and kernel linear. So kind of interesting. It chose a relatively simple model. Let's see if this actually performs better than the default values. So we're going to say that we have our grid predictions. So grid predictions is equal to grid.predict off scaled x test. Run this. Now that we have our predictions, let's go ahead and compare them to the original test values. So we're going to say mean absolute error that we already imported and compare y-test to our grid predictions. So run that, and you'll notice now our mean absolute error is 2.51. The base default model, that mean absolute error was 5.23. So we are improving quite a bit. Let's go ahead and copy this for the root mean squared error. And instead of base predictions, we are going to run this grid prediction, run that, and you can also see that we substantially improved the root mean squared error. So definitely, when it comes to support vectors, both for classification and regression, you should be both scaling your data and performing a cross-validation and a grid search for the best parameters. It's really hard to have an intuition for many different data sets over what are reasonable values for C, epsilon, gamma, etc. So really, since the computer's doing the work, set this up at a time that works for you when you're going to be away from your computer, maybe right before you go to sleep or when you go on a lunch break, and have the computer do a really large parameter search for you to figure out the best model, since support vector machines almost always need some sort of grid search to figure out the best parameters. Okay, now that we understand how to perform support vector machines for both classification and regression, it's time to test your skills for a project. I'll see you at the next lecture.